Okay, so before we start with that problem, let us see some of the things that we have been talking about, and we have been talking about latest Snapdragon processor. I mean, this is not too old. I mean, this is something 2018-19 and went up to 2020. Now we have got Snapdragon 865. So it has got the CPU, it has got GPU, and I've talked about manufacturing process. This is 10 nanometer process, low power, and this is 7 nanometer process, again low power. Now, as you can see, it has got 512 KB of L2 cache, which is for this large A76 derivative, which is running at 2.84 gigahertz. Then there are three smaller ones, again, same A76, but running at lower speed, 2.42 gigahertz. And there is a 256 KB cache. There's a smaller cache for this three processors, L2 cache. And then there are four little brother. So these are known as this one and this three. They are known as the big cores, and this is known as the little cores. So this architecture is called as big little architecture. So big means so this is big little architecture, and this A76 is considered as a powerful processor, and you can see it from the speed that it is running at very high speed. One of them is supercharged out of four, so which is running at 2.484 gigahertz, whereas other three are running at 2.42 gigahertz. So this four of them form big processor, and this one forms a little processor. Now, why do you need big and little? The reason for having big processor and little processor is that when you have a heavy load, for example, if you're playing a video game or doing some camera processing or something AI thing, beautifying your photograph or something, then you require power of these four big cores. For the smaller things, your routine, say just checking for downloads or just browsing the net, you don't require a too big processing power. So you use just A55, Cortex A55 made from ARM, which is only running at 1.8 gigahertz. And as you know, that power is directly proportional to frequency. So higher the frequency, more power usage. And that is the key thing. You don't want to use up too much power. You want to use as little power as your phone can do with. So 1.8 gigahertz, if the things can be managed with 1.8 gigahertz processors, then it's great. If it becomes too much for it, then it switches on the large core processors. So here there are L2 cache, which is like 1 into 512, and there are 3 of 256 KB L2 cache, and there is a 2 MB L3 cache. They have not given any details regarding L1 cache. It's proprietary, so they may not want to share that knowledge with us. So basically, I just wanted to let you know that what we are thinking is sort of realistic, what we are talking about. So this is like this. This is running at 2.84 gigahertz. This three are running at 2.4 gigahertz. They're all A76 ARM Cortex, and these are for A55. Now this is known as asynchronous thing that I mean these three previously what used to happen was that, everything was supposed to run. If it is A76, all A76 core has to be of the same type. And then, A55 is supposed to be of the same type and speed. But now, you can, ARM is allowing you to do mix and match. You can have one A76 and 7 A55s, or two A76 and 6 A55s. I mean, any which way you like, you can choose. Now, so this is like conventional big little core, and this is their dynamic big little. So what they are trying to say is that, you can have one big core and two little cores, or, one big core and four little cores. I mean, whatever you want to say. So, but this is asynchronous architecture where, not everything is the same. Not all the cores are of the same number. Okay. Now, the data which I had available, it was from the first generation of Crate, that is Crate 800, which came out in 2016 or 17. So what we call it L1 cache, they call it as L0 cache. So here it is 4 KB and 4 KB. So that is direct map cache. And it is running at the core frequency. Then there is L1 cache, which is 16 KB and 16 KB. So they have got two caches, which has got separate instruction memory and data memory. But this one is four-way set associative. And again, that is running at core frequency. And L2 is 1 MB for dual core or 2 MB for quad core. And those are A2A set associative, and it is running at 1.3 gigahertz frequency. So this is the general formula. Again, why we are checking AMAT. So let us just refresh why we are doing this. Okay, so last time we did talk about that this is patch, this is decode, this is execute, this is data memory access or memory, and then this is write back. Two of these, this one accesses instruction memory, this one accesses data memory. So then, I mean, the speed of access determines, how fast your processor can run. And as we have seen, these two things, if you don't get what you're looking for in L1 cache, and if you have to go to L2 cache or beyond, then this time would be really out of bound, and your processor will become extremely slow. So we need to find out, I mean, we have to give some idea to the customer that, how fast that person's program would run. So what people would do is, take a general purpose program and, find out that, what would be L1 hit rate. And then, basically L1 hit rate is like 100 minus L1 hit rate is L1 miss rate. So that, what percentage of instructions will have to go to L2. And then, what is L2 hit rate? And, 1 minus L2 hit rate is L2 miss rate. So basically that will give what percentage would go to main memory. Okay, so this is what we are looking for. And now we are looking for a formula that is average memory access time that is equal to, and this is your standard formula. This is for two-level cache. And, once I explain this, I would like you guys to do it for, say, four-level cache. So let us see this thing. This is a shortened version. So basically what this is doing is that, time for L1 hit. So time for L1 hit plus miss rate of L1 multiplied by time for L2 hit plus miss rate of L1 multiplied by miss rate of L2 multiplied by main memory access time, which is same as L2 miss penalty. So that is this one, you can call it time for main memory hit. So let us understand this. Time for L1 hit usually is 1 cycle. It is designed in such a way that, if it is a hit, it will run at 1 cycle. So, I mean, the same frequency as the processor frequency. If it has to go to the second level, then, you get miss rate of L1 multiplied by time for L2 hit. So miss rate of L1 and this time for L2 hit is same as miss penalty of L1. Remember, we saw the original thing was that, is equal to time for hit plus miss rate into miss penalty. So this is similar to that, or just, it is the same thing, but, miss penalty of L1 is same as time for L2 hit. So for example, if you can't find it in L1 and have to go all the way to L2, then, it will be a 10 cycle penalty. So either you can call it miss penalty for L1, that is 10 cycles, or time for L2 hit, which both of them mean the same thing. So here also, I have said miss rate of L2 into, I could have written miss penalty of L2 or time for main memory hit. This is, say, 100 cycles. So you can put it as time for miss penalty of L2, and that is 100 cycles, right? So now can you just extend it for L3? Suppose I have used L3 cache. What would be the term which would be used for L3? Okay, I'm giving you 2 minutes time to think. I want everyone to do it. Just look at this formula. This is for 2-level caches, L1 and L2. What if there is a 3rd level cache? So if there's a 3rd level of cache, let me give you a hint. This, you should call it as time for, this should be, if it is 3 level, then, here I would put it as L3. If I have 3-level cache, and plus there would be additional terms. So what would that be?
Sir,
Yes.
it will be miss rate of L1 multiplied by miss rate of L2 multiplied by miss rate of L3 multiplied by average access time of main memory.
Okay. I mean, what do other people think?
There will be L3 hit also.
Yes, sir.
Hello?
After miss rate of L2,
Miss
Say
rate
that again,
multiply by
L1.
time.
Just the term of L2 miss penalty will change, and uh, and L2 miss penalty, instead of that, the term will be time for L3 hit plus miss rate of L2 cross miss rate of L3 cross L3 miss penalty.
Okay, so let me just understand from you guys. So I got first the time for AMAT is equal to first term is L1 or hit time for L1, okay, plus second term was miss rate of L1 into miss penalty of L1, right? Either I write miss penalty of L1 or if miss penalty of L1 or miss or hit time for L2. I mean, both of them mean the same thing. Plus the third term was miss rate of L1 multiplied by miss rate of L2 multiplied by miss penalty of L2. And this miss penalty of L2 would be same as time for L3 hit. Now this is the third term we are talking about, right? You know, this three terms we had already seen. So what would this be? So correct me if I'm wrong. Multiplied by okay, is this correct?
Sir, it will be main memory hit.
Well, miss penalty of L3 is same as time for main memory hit.
Okay.
Right, so time miss penalty of a previous level is same as hit time for the next level. Does it make sense? Does anyone have any problem with this?
Sir, I suppose there will be plus sign in between last two terms. Miss penalty of L3 and miss rate of L3.
Why should there be a plus term? I don't understand. See, the original thing which we were thinking of is time for a hit plus miss rate into miss penalty. Now, miss rate into miss penalty. Now, this thing is like now it has got multiple levels. So time for a hit is constant one cycle, that is for L1. Plus, these are the other things, right? So time for a hit one cycle plus if miss rate is zero, then then the whole thing is going to be zero over here. So this is like everything would be running at one cycle, but miss rate of L1 is never zero. So then you would start getting the numbers.
Yes, sir. It will be multiplication. Yeah.
Okay, so let us see a simple understanding. Now, I'm saying that L1 cache has hit rate of 10%. L2 cache has access time of 10 cycles. So basically for L2 cache, the access time, that means it is from L1 to L2. Also, I need additional information that L2 cache has, sorry, I should have written hit rate of 90%. 10% is too little. So hit rate is 90%, right? Then I talk about main memory. So main memory we assume is the last level of memory. So there is no question of hit rate being anything less than 100, because if it is not there, it is nowhere. So I don't write the hit rate for main memory. I assume it is 1. Correct? 1 means 100%. So only I would say is that main memory access time. And when I say this, it is understood it is between the previous level to this level is 100 cycles. We usually talk in terms of cycles because, then the processor speed does not matter. If the speed is higher, then cycle time would be lower. But, one cycle would remain one cycle. Only the time would be changing. That, previously for a slow processor, one cycle would have meant 3 nanosecond. Whereas for faster processor, one cycle may mean 1 nanosecond. And, very fast processor, it may even mean 0.33 nanosecond. So now let us say, I'm saying this is hit rate is 90%. This is also 90%. So I'm going with, say, 100 instructions. And suppose these are all, I'm talking only about, let's say, data. I've got 100 data to access, right? So based on this information, in my L1 cache, how many data accesses would be a hit out of 100?
90.
Okay, 90. So you will find your 90 accesses would be found. So it will just take one cycle. So it will be running at processor speed. And 10 data references will have to go to all the way to L2. Right? They have to go to L2. Again, L2 has a hit rate of 90%. So how many data accesses which has come here will be found in L2 out of 10?
9. So on average, you can say 9 accesses will be hit.
Right. So 9 references, data references would be found in L2, and 1 reference would go all the way to main memory. Okay. So this is what it means, having a 90% of hit rate in L1, 90% of hit rate in L2, and then, final thing is main memory. We are just stopping at main memory. So, if things are not there in main memory, it is nowhere. So if it is not found in L1 or L2, it has to be in main memory, or else it does not exist. So the hit rate becomes 100% for main memory. So whatever references we give, either, it is found in main memory or it is illegal. So exception would be thrown. Okay. Is this clear? The concept of hit rate and how to go beyond. And, you can also do the example, this miss rate into miss penalty. So even if the data is not given, time to access, if the data is found in L1, so time for a hit in L1 is usually 1 cycle unless something else is given. Is this correct? Okay, now before we move forward, someone has asked a question that what is A76? And I was referring to the processors, I mean, these are basically the marketing names which are given. So Cortex A76 is a processor identifier. That particular processor has some particular kind of frequency, particular number of cores, particular L1 cache size, particular L2 cache size, particular L3 cache size. So the identifier given to it is numbered. A is general Cortex A series. And then after A, you put an identifier, which is 76. It does not go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are multiple reasons why, from A55, you get A72 directly. And then there is 75 and 76. So there might be internal reasons why things are named like that. But this A76 is a marketing name given by ARM to sell this processor to its users. Does that answer your question? Okay. So let us move forward. Now let us look at this. So, I mean, this is the kind of memory architecture we are working with in this particular problem. It has got L1 instruction cache, L1 data cache, then there is L2 unified cache, and then there is main memory. Okay, so this is the memory architecture we'll be using. And we have been given a terribly wordy problem statement. And I necessarily gave it to you so that you learn to separate out the important facts or important details from this particular long write-up which is given to you. Okay. So first thing, it is saying that it has given separate instruction and data cache for first level. So that's why we have drawn like this: L1 instruction cache, L1 data cache. Then it says a unified second level cache. So this is, we have drawn a unified second level cache. Okay. The first level cache is a direct map, write through, write allocate cache with 8 bytes of data total, 8 kilobytes of data total, and 8 byte blocks, and has a perfect write buffer. So, forget about that particular thing, not very important at this point. So it's saying that, L1 cache is direct map. And, we have been saying for all along that, L1 cache is 99% a direct map cache. And the reason for that is the purpose of, so now at this particular point, you will see what is the main purpose of L1 cache and what is the main purpose of L2 cache, because it's a design criteria. So what are the kind of things you want in designing L1 cache versus what you need to remember while designing L2 cache? So L1 cache is always designed keeping the seek time minimum, right? Why? Because you have to run it. If the data is to be found, it has to be found in one cycle. So you are trying to reduce time for a hit as much as possible, so that you want to bring it to the processor speed. So L1 cache does not carry about miss rate, and generally L1 cache has higher miss rate. And it is understandable. It is using direct map cache, which is quite inefficient, and there might be a lot of misses. But the purpose of L1 cache is not so much to reduce the miss rate, but to reduce the time for a hit. And L1 cache can afford to have a high miss rate because L2 cache is quite close to it. Means there is not too much penalty to go from L1 to L2. It is only 10 cycles, right? So L1 cache may have higher penalty because it is specifically designed to reduce time for access or time for a hit. L2 cache, on the other hand, is designed to reduce miss rate as much as possible because there is a big gap between L2 cache and main memory, say 100 cycles. So that's why you may say that, L2 cache may take some time to, find the data, which is like 10 cycles to find to either say I found it or say I did not find it in L2. But in main memory, we are certain to find it. So L2 cache is designed in such a way so as to reduce the miss rate as much as possible, even though the seek time becomes slightly more, or a time for a hit becomes more. So this is the data which is given. This then also given furthermore force level. So here the information is given about the force level data cache, and what is it? Direct map, write through, write allocate. Size of it is 8 KB. And block size is 8 bytes. Okay. Whereas for instruction cache, it is direct map. Size is half the size of data, so it is 4 KB, and block size is same as 8 bytes. The second level cache is two-way set associative, write back, write allocate cache with 2 MB of data total and 32 byte block. So then once you get this, you should start filling in the data over here. So any data which is relevant to instruction cache, you write under the heading of L1 instruction cache. Then any data which is relevant to L1 data cache, that you write under L1 data cache. Any given data which is pertaining to this L2 unified cache, you write underneath it, and so on and so forth. And that you start separating out the important details which is given in this particular problem. Does anyone have any question up to this point? Okay, so let's move forward. Now this is given, so this is, and then for second level cache, which is two-way set associative, write back, write allocate, with 2 MB of data total and 32 byte block. So block size is bigger over here. Now there is some more information is given about force level instruction cache. It's a miss rate of 2%. So instruction cache is very, very good. It has got 98% hit rate. The force level data cache has a miss rate of 15%. It usually happens that instruction cache has much lower miss rate because there is a branch prediction mechanism, and then usually your instructions are not jumping around too much. Whereas the data, there is a problem that data may be dispersed around. So data cache usually has higher miss rate. So it is given here that first level data cache is miss rate of 15%. As opposed to miss rate of only 2% for instruction level cache. The unified cache has a local miss rate of 10%. That is miss rate for all accesses going to the second level cache. So it is a miss rate of 90%. So in other words, hit rate of 90%. Assume that 40% of all instructions are data memory accesses, out of which 60% of these are loads and 40% of stores. Assume that 50% of the blocks in the second level cache are dirty at any time. Now, first, before you understand, you should start writing down the data underneath a given heading, and then, later make sense out of it. So, first question is, what fraction of all data memory references causing a main memory access? So, look at here. I have put down things in red. You can, when the you can put, you underline it or do something, but these things should catch your eye. That I'm talking about first level data cache. This, and this is associated with it. Same thing with instruction cache, and this is all for second level L2 cache. You had written about miss rate, then this important data. So I will see this little later. I'll come to this, but first, this is how you should Right, how to interpret data. As I was saying you, L1 data cache. What are the things which is associated with it? The size of the L1 data cache is 8 KB. Its block size is 8 bytes. It is direct map. It is write through. It is write allocate, and miss rate is 15%. L1 is, and this is all from the data which is given as we detected in the problem statement which was given to us. Then this L1 instruction cache, the size is 4 KB, the block size is 8 bytes. It is a direct map cache and miss rate is only 2%. L2 unified cache, of course, size is 2 MB, it's a large one. Block size is 32 bytes. This is two-way set associative. It's a write back kind of thing as opposed to this write through. Why nothing is given over here, whether it is write back or write through? No data is given for this L1 instruction cache.
Sir, because we do not write in instruction cache. We
Correct.
only read in that.
Correct, right? So instructions are there for the processor only to read. Processor is not allowed to make changes in your program, right? That is your job and probably compiler's job, but definitely not a processor's job. So there is nothing to do with write. So you only load instructions. You never quote unquote store instruction. Okay. So this is the data. Then 40% of all instructions are data memory accesses, out of which 60% are load and 40% are store. So what is load associated with? What kind of operation? Is it read or write?
It is read.
Read.
Reading
Okay.
from memory to registers.
Correct. So loads are associated with reading and store is associated with write operation. Okay, so that's why they say that 40% of instructions are data memory accesses. So what does exactly that means? So that means if you have a 100-line program, out of which 40 instructions would be load store type, and within that 40%, 24 instructions would be load type, and 16% would be, or 16 instruction would be store type. Okay, so that is what this whole data means. And finally, that 50% of the blocks in L2 are dirty at any time. Now look at this. Why this word dirty has come? Now the reason for that is that we have said that your L2 cache is a write back kind of cache. So what it means is that when something is written into L2, so L1 writes something into L2, you will not immediately go to main memory and change it. Okay, you will just mark it as dirty. And when that particular block is to be thrown away, and then that block is called a dirty block in which a change has been made. And this memory controller has to remember that whatever was that particular dirty block in L2 has not been updated into main memory, right? Updation works downwards, right? So processor makes change and first stores it in L1, and then at a particular time, if it is write through, whatever is written in L1, you immediately write in L2. So the policy of write through for L1 is only between L1 and L2. Okay, so if L1 says I have got a write through policy, means whenever a change is made in L1 data cache, it will immediately make change in L2 data cache, but it will not go to main memory and make immediate changes in main memory. That depends on L2's policy, write policy. So L2 has write back policy. So what it means is if some change has been made into L2 block, it will not go immediately to main memory and change it, but it will just put a flag of dirty bit, or it's a dirty block flag, and then would change it only when that particular block has to be replaced. So if a block is to be thrown out from L2, then the memory controller first checks that whether there is a dirty flag on that block. If the block is dirty or if the dirty flag is on, that means it would first copy it into main memory and then only it would kick it out or throw it away or wipe it out. Is this clear?
Yes, sir.
Okay. Now just give me 1 minute. Okay. So this is what the data means. So this now, if you can come to this point, the things have become much easier. But everything is loaded. I mean, what would be the effect of doing this thing right through? This is all write allocate. And this is also write allocate. So what does write allocate means? That means if you are looking for a particular memory to write into, and if that particular memory word or that block containing that memory word is not present, then you bring it from the next lower level and then you write into it. And no allocate would have meant you put it into buffer and then later on you will see. Okay, so if this is clear, then we move forward. Now, what fraction of all data memory references cause a main memory access? Now, if you just write this, you will miss a very important point. Now, what we are saying here is that from the data, it is clear that L1 data cache is a write-through cache. That means any change, or that whenever you execute a store instruction in L1 will have to be written immediately to the next level L2, right? So here's a very important conceptual point. So since it is a write-through cache, since L1 data cache is a write-through cache, that means whether you find the data in L1 or not find the data in L1, for both cases, you will have to go to L2. If you found the data in L1, then you will have to go to L2 to write it over there also. If you don't find the data in L1, then naturally you will have to go to L2 looking for that particular block. So the important conceptual point here is that if it is a write-through cache, then every write reference to L1 cache can be treated as L1 miss, whether you found it in L1 or not. Is this sentence or is this assertion clear to everyone? Does anyone have any doubt in this one? If you have any doubts, please speak up. Okay. So here what it means is that any change in L1 will have to be written immediately to next level L2. So in other words, all L1 stores can be treated as L1 misses, since for each store in L1, it has to go to L2. Now, two things. We have been given loads and stores, two different references are given. So when it is a load, it is not a write operation, it is a read operation. So if you look at here, that when you have a load operation, when you have a load operation, then you do percentage of data references that are load multiplied by L1 rate miss rate into L2 miss rate. So this will be a fraction which will have to go to all the way to main memory, right? Just like this very simple problem that we did. That we have got, suppose I say that, I've got 100 data references, or say instruction in, 100 data references. 90% is the hit rate of L1, 92% is the hit rate of L2. What percentage would go to main memory? So what do? We say miss rate of L1 and miss rate of L1 would be 0.1% multiplied by miss rate of L2 is again 10%. So it is fraction wise, it is 0.1 multiplied by total number of data references, which is 100. So this thing will give you that, for one data reference, you will have to go all the way to main memory. So it's the same as what we found it through observation, but this is a more technical thing or technical way of putting it. So that, total number of references multiplied by L1 miss rate multiplied by L2 miss rate. And that would be that many references will be going to the last level, that is main memory. So that is 1. So very similarly, that is what we are doing here. That, percentage of data references are load. So that is, what is the load percentage? It is 60% multiplied by L1 miss rate is 0.15 multiplied by L2 miss rate is 0.1. So this is for all the load operations or the read operations. And for write operation, you can see L1 miss rate I'm taking as 1. Right, I'm not written over here. It is assumed that, it is 1 because, we don't write multiplied by 1 anywhere. But, if you want to explain it to me in your exam paper, you will say 0.4 multiplied by 1 into 0.1. So this is L1 miss rate is taken as 100%. So that is taken as 1, and L2 miss rate is 10%. So it is written as 0.1. So total miss rate due to both is around 4.9%. Is this clear to all?
Sir.
Yes. You
Sir,
said
how
yes,
is-
sir, or you have a question?
Sir, how is L1 miss rate 1 over here?
I'm sorry, say that again, please.
Sir, how is L1 miss rate 1 over here?
Okay. So L1 miss rate 1 means 100% misses. Now we have written this 100% miss rate for L1 is for this reason. That, from data it is clear that L1 data cache is a write-through cache. So whether you find the data in L1 cache or not find the data in L1 cache, you will have to, either way, you will have to go to L2. If the block which you are looking for to write into is found in L1, then, immediately you will have to go to L2 to also change it, because write through cache means as soon as you make change in L1, also make change in the next lower level, that is L2. So you will always have to go to L2 no matter what for a data reference. Is it clear?
Yes, sir. Yes, sir. Now it is clear, sir.
Okay. So that's why you write 1 over here. I have not written it, but, please, you find out, or, you just write this multiplied by 1 multiplied by 0.1 plus here that is straightforward 0.6 into this is 15% and this is 10%. So for read it is common that if you find the data in L1 you don't have to go to L2, right? Because reading is reading, you are not changing anything. Okay. The question 2 is how many bits are used to index each of
sir.
the cache? Yes.
Sir, we also have that 40% of instructions are data memory accesses. So we should not multiply all this by 0.4.
Then what should we do?
Means multiply 4.9% into 0.4. Should
Okay.
it not be like that?
I understand your problem. But read the question which is asked carefully. What fraction of all data memory references causes a main memory access? That means whatever number of data memory references which are given. So you are only talking about data memory references, right? So you are not saying that you're not talking about other 60%. You are talking only about the 40% of the thing, that is your 100%. And out of that, how many, what time will be taken, or how many references from that will go all the way to the end? That is only what you want. So when I say that what fraction of all data memory references needs to go to main memory, you assume that if the data memory references are 100, how many will go to main memory? Right? So there is no, you don't take or consider those instructions which does not have data memory reference.
Yes, sir, got it.
Yeah, so you don't talk of those 60% which are non-data memory references. So that is out of the picture. So your 40%, whatever remains is your 100%. So that is all data memory references. And out of those data memory references, what percentage goes all the way to main memory? So this is how you find it. Is it clear?
Yes, sir.
Okay. The second question is pretty easy. I guess you guys can solve it. Can someone give me the answer that how many bits are used to index each of the caches, that is instruction cache, data cache, and L2. So L1 instruction cache, L1 data cache, and L2. Can you just write down, don't speak the answer. If you want to tell me the answer, then you can write into the chat window. But I want at least 15 people to answer this question to me. And the data you can see, sorry. So basically, how many bits are used to index each of the caches, that is instruction data and L2. And this is the, whatever the gist of the overall problem which is given to you. So basically, you want to find out total index bits used by L1 instruction cache, L1 data cache, and L2 unified cache. I hope you guys are doing it and not waiting for me to give you the answer. Anyone? How come I'm not seeing any answer? You can write it in chat window. Okay. So there are some people have written the answer. So let's see what I have done. So data cache is 8 KB, and each block is of 8 bytes. So total you have got 1024 blocks. So you have got 2 raised to 10, right? That is equal to 10 bits. Now for instruction cache, it is half the size, right? Just 4 KB. So this would give you, but the block size is the same. So it is 512 blocks. So that is 2 raised to 9, so 9 bits. And L2 cache, it is of 2 MB, and you divide it by the block size for L2, which is 32 byte. So that means it is 32K sets. And so that is equal to, why have I said 32K sets? Because this is two-way set associative, right? So if you want to look at this, it is 2 MB is 2 raised to 21, 32 byte is 2 raised to 5. So this is 2 raised to 16. But this is not direct map. It is two-way set associative. So there will be equal two halves, put side by side. So that means divide this by 2. So that is equal to 2 raised to 15. So that means 15 bits are used for index for L2 cache. I hope everyone got it. So those of you who wrote 16 bits as the last one, you should change it, because we are talking about two-way set associative. Suppose if it was four-way set associative, then what would be the total number of index bits?
Then 14 will be the answer.
14.
I'm sorry. How much would that be?
Sir, 14.
Okay. Right. Okay, good. Now the third one, and this one is a long one. Now this one says that what is the average memory access time in cycles? So this is like, final answer, that what is AMAT in terms of cycles, not in terms of time. Now they are saying that total memory accesses here. What is the total memory for 100%? Suppose, let's not talk about percentage. Let's talk about like a lay person. I've got 100 instructions. Okay, I've got a program which has got 100 instructions. And as you can see in the data, that 40% of all instructions are data memory accesses. So total, how many data access, how many memory accesses are made, both instruction and data together?
40.
Right. So total you are making 140 accesses to memory. 100 to instruction memory. Why 100? Because it's a 100-line program. And we have been told that 40% of all instructions are data memory accesses. That means either it is load or store. So either it could be. So 40% of the times we will be going to data memory. 100 times you are going to instruction memory, because even load store instructions are instructions, right? So every instruction will have to be fetched. So if there are 100 instruction program, 100 instruction will be fetched. And then if the 40 instructions are either load or store type, then you access it 40 times. So total memory accesses, which includes both instruction and data, is 100 plus 40. So that makes it 140. Is this clear to everyone? If you don't understand, please ask me. Okay. Now let us move a little forward. Now, out of this 100 instructions, you have to find out AMAT individually, AMAT for instructions, AMAT for load, and AMAT for store, right? Because all three AMAT would be different because the data is different. But they have to be weighed down by the correct weighing factor. That total memory accesses are like 140. But out of 140, 100 are instruction accesses. So if you want to do a weighted average of AMAT, you multiply AMAT instructions by 100 divided by 140, right? So that would be overall AMAT due to instruction. For AMAT load, you will say 40%, sorry, 60% of the 40%, right? 40% are total data memory accesses, out of which 60% are load. So 0.6 multiplied by 0.4, that is equal to 0.24. So 0.24 or 24 divided by 140, you use that weighing factor and multiply it with average memory access time for a load instruction. And by the similar argument, 0.4 multiplied by 0.4, that is 16, or 4 into 4 is 16, divided by 140. So that weighing factor should be multiplied with AMAT store. This is again a very important conceptual point which you should take into account. Okay, so this is the weighted average. Now we missed out one important thing here. I forgot to mention the size of the bus. This we did not consider. See here, the size of the bus is 64-bit. So remember, I was telling you that if you are transferring a block, the size of the bus would be a determining factor how fast a block would be transferred from L2 to L1. Now L2, what is the block size for L2? The block size for L2 is 32 bytes, right? So 32 bytes is 256 bits, right? So here you want to transfer 256 bits, but the size is only 64-bit. So you will have to make 3 additional trips. So the first trip would take 10 cycles to bring the first load, that is 2 bytes. Sorry, 2 words, or that means 8 bytes. You will be bringing 8 bytes after 10. Then at the 11th cycle, you will be bringing another 8. At the 12th, another 8. And in the 13th cycle, another 8. So total 32 bytes would be transferred. Is this concept clear? So this explains that limiting size for my block could be the bus size. If my bus size is very small and if my block size is very large, then it would take a lot of time to a lot of cycles to transfer a block from L2 to L1. Here the size is 128-bit. So 128-bit is how many bytes? 16. So main memory has 32 bytes. So if you want to transfer 32 bytes over here, then it would take 1 cycle plus another 1 cycle. So 100 cycles plus one cycle. So 101 cycle it would take to transfer one block of 32 bytes. Is this clear? If you don't understand it, please ask me. So this does explain the importance of having a wider bus. Otherwise, your performance would suffer. So now you are definitely going to use this particular time, that L1 hit time plus L1 miss rate into this. This is writing in more concisely. If you don't understand this type of thing, then you better use the way which I have written, so then that it would not leave any confusion. So this is how I wrote that miss rate. The first one is hit time for L1 plus miss rate of L1 into miss penalty for L1 plus miss rate of L1 into miss rate of L2 multiplied miss penalty of L2, and then this. So this would not leave any confusion in your mind. But if you want to write in a compact way, then this is the compact way to write. So the memory transfer time is just, I have explained, the size of the bus between L2 and memory is 128 bits, that is 16 bytes. And each block has 32 bytes. So that means 100 cycle will be used to bring in the first 16 byte, and the next one cycle will be to bring in another 16 byte. So the total cycle to transfer 32 byte block is 101 cycle. Fortunately, your block for in L1 and L2 is only 8 bytes. So 8 byte is 64 bit. And thankfully, this is a 64 bit bus. So you just have to make one cycle, the whole block will come, because block size is only 2 words or 8 bytes. And the size of the bus is perfect to transfer 8 bytes in parallel. So if you want to transfer one block from L2 to L1, it will take only 10 cycles and not 11 or 12 or 13 cycles. Is it clear? Okay. So now we need to find out these 3 things first. Forget about this weighing factor that we will address later. We are just, first of all, we are looking to find out AMAT instruction, AMAT load, and AMAT store. So this is a weighing factor which I've told. Now this, I think you will have to change, because there is a problem in one of this, and if you do it this problem yourself, you should be able to figure out where is the problem. Okay. Also, I have used 101 cycles over here, and I have multiplied it with 1.5. So why am I using this many number of cycles rather than just 101? Why I'm using 1.5 into 101? And the reason for that is clearly given over here. That 50% of the blocks are dirty. That means they have been changed. Now L2 is a unified cache, and the write policy between L2 and main memory is write back. So that means when you want to transfer 10 blocks from main memory to L2, and then what the data says is the 50% of the blocks are dirty at any time, because when 10 blocks are coming from main memory to L2, and when L2 is filled, you will have to throw away 10 blocks to make space for the 10 blocks coming from main memory. So the 10 blocks which have to be thrown away, out of those 10 blocks, 5 blocks are dirty. So first you will have to, before you bring in the 10 blocks this way, you have to first write back 5 blocks into main memory from L2 to main memory. Once those main memory blocks are updated, only then you will be able to bring in the 10 blocks from main memory to L2. Right? So total transfer taken would be 15 blocks, whereas you require only 10 blocks. So that means every time you will have to do 1.5 times more work than just doing it one way. So you'll have to go say 100% from main memory to L2, then 50% will go back from L2 to main memory because it's a write back thing. And 50% of the blocks are dirty at any time is given in the data. So that's why we are writing 50% back. So I have left this over here. You can look at this and this things are not correct over here. So don't take this as gospel value. I want you to come up with the correct answer. Usually, I keep this as an indicator. When I ask students in the class to do this problem, if they have seen the seniors thing, in fact, just write down these answers. And, then I can immediately tell that, they have not done it themselves. They are just copied the answer from previous year thing. So take a look at this. And, we will discuss this again on Wednesday. And then, probably you will tell me the correct answer. What is the correct answer over here? Okay, does anyone have any question up to this point before we stop?
Sir,
Yes.
so can you explain once again that if we have a penalty of 100 between L2 and main memory to again bring the another block through the bus, why are we only adding 1 + 1 cycle?
Okay. So these two things are separate. So first, why are we considering 101 cycle? So now the answer can be gotten from here. This is the 128-bit bus. Okay, so that means 128-bit, or that means how many bytes? 16 bytes can be transferred in parallel. The block size in main memory and L2 is 32 bytes. Correct? So according to the data given, that the first hit, the main memory access time is 100 cycle to the first bus width of data. Okay. After that, the memory system can deliver consecutive bus widths of data on each following cycle. So in 100 cycles, we will get the first 16 bytes, and to get second 16 byte, we'll have to wait for one more cycle. Okay, so that makes it 101, 100 plus 1.
Yes, sir. I was having the doubt that we are adding only one. The doubt I had was why it is not 100 plus 100 to bring the second block.
No, that's what it says, no? Because it is given here that the in a large memory system, most of the time is spent in looking for the block. So as I told you, if you go to the library, most of the time would be spent by you to find out a particular row number, where your subject area books are there. Once you reach there, then all the books are, in your area, say operating system or computer architecture would be placed side by side. And, if it is nicely done, then, all the books which are part of your computer architecture or computer organization course would be right next to each other. So finding the first book will take you the longest time, but finding the second book will not take you much of a time. So that's why locating the first block, locating the block would take up the maximum number of time. So that is 100 cycle. But in 100 cycle, within that 100 cycle time, what is accounted for is that, you will bring back the first bus load of data. And that is, but bus width is only 16 bytes. but you know, your block size is 32 bytes. So once you've located it, then you know, the only question which remains is to how quickly you can bring the other 16 bytes. So that is taking one cycle, and it is given over here. After that, the memory system can deliver consecutive bus widths of data on each following cycles. Does that
Okay,
answer
sir,
your question?
understood. Yeah, yes, sir.
Okay. Anyone else? Okay, so we stop here. And you know, we will start